Welcome to topic 10.3. In this topic, we are going to look at the general characteristics of acids and bases and the theories behind them. One common feature we're going to find in all acid theories is that they have the presence of the hydrogen ion, specifically the hydrogen cation. One of the things I want to note is throughout this set of lessons is that hydrogen and proton are going to be used interchangeably. You'll see that with other texts and videos and things like that, because hydrogen, if you recall, is made up of only one proton atomically. So we can kind of say proton and hydrogen and be speaking the same language. One thing that's common of acids is for them to have a sour taste. Citric acid is present in citrus type fruits. Vinegar has acetic acid in it. Soda has carbonic acid, and that's where they get their sour taste from. We don't really have time to invest into electrolytes and non-electrolytes, but just as a note, acids are ability to conduct an electrical current, making them an electrolyte. Acids have the ability to change the color of an indicator. Indicators can change different colors depending on what they are, and the strength of the acid, or in here soon, the strength of the base will decide how it changes colors. Litmus paper, there's blue and red litmus paper, and those can change just one color. Litmus is useful for just telling us if something's acidic or if something's basic, but that's as far as it goes. Phenolphthalein, you guys have seen that before first semester when we did our chemical changes lab. It turns pink, otherwise looks colorless. Universal indicator, as shown here in the image, changes colors over a wide range of pH values. It stays in the cool color range as something is greater than 7, and acids, which fall below a pH of 7, fall in the warmer colors with a little bit of green tossed in there. So what we find that when we combine an acid with a base, it results in the formation of water and a salt. Bases have hydroxide ions, and we'll explain more with that here momentarily. They are notorious for having a bitter taste to them. They're present in a lot of household cleaners, soaps, things of that nature. There are many medications that you maybe would take for an upset stomach that also contain a base as a way to neutralize excess stomach acid in the stomach. They also, like an acid, can conduct an electrical current because they are an electrolyte. Like acids, they will change the color of an indicator. Again, depending on where they fall on their pH, we can use different indicators for different purposes, and hopefully we have some time to talk about that. Because they, again, contain hydroxide, many bases have a slippery feeling to them, which is the whole reason behind soap and the whole reason behind, like shampoos and things of that nature, having that soapy, slippery feeling. Their pH is greater than 7, and again, when they react with an acid, it is a neutralization reaction, which is another reaction type. We just don't dive into that during our reactions unit, just to kind of keep it from getting to be an overwhelming amount of information to process. The next thing we're going to look at is the theories behind acid-base categorization. So Arrhenius is the first theory to come along on determining what do we call an acid, what do we call a base. And it has its pros, but it has its cons as well, in that the main issue with it is it's exclusive and leaves things out that we will later find out should belong into the category of being a base. But in terms of acid, it's pretty much good to go. If we see a hydrogen cation present, that means it's acidic. So here we can see HCl. This is the dissociation equation of HCl, where hydrogen chloride or hydrochloric acid, I should say, dissociates, breaks apart into the hydrogen cation and chlorine. So because it has this hydrogen ion present, that means it is an acid. On the other side, an Arrhenius base is one in which it forms a hydroxide anion. So here's the dissociation of sodium hydroxide into the sodium cation and the hydroxide anion. And so he defined these again with the hydrogen and hydroxide. Again, there's an issue in that it narrows out and restricts what we classify as a base. There are a couple of bases we see very frequently based on their pH. We know ammonia and sodium carbonate, for two examples, do not have the hydroxide, even though they are pH-wise in the base range. And so we had to evolve our definition of what is a base into a more accepting term. That leads us to the Bronsted-Lowry acid base, and we're going to just classify these two real quick. It asks here which substance can be classified as an Arrhenius acid. We have HCl, NaCl, LiOH, and KOH. So the only one that can be an acid is example A, letter A, because it has the presence of the hydrogen cation. The next question is now asking for an Arrhenius base. We have HCl, NaOH, LiNO3, and NaCl. The only option there is letter B for sodium hydroxide because it has the presence of the hydroxide anion. So a Bronsted-Lowry acid and base is something that is, again, more broad and more open to what we categorize as these three types. So we say that a Bronsted-Lowry acid is something that is donating or a donor of the hydrogen ion. If you're an organ donor, if you're a donor of money, if you go to donate something to a thrift shop, you are again giving away. So a hydrogen ion donor is one that is releasing or removing a hydrogen from its formula. A Bronsted-Lowry base is one that is then the acceptor. So the main thing that's really going to differentiate here is that the base opens up the idea that it does not have to be hydroxide to be considered a base, but rather did they take and accept a hydrogen ion to its mix, to its formula. So here we just talked about acid base, and we'll explain and differentiate conjugate acid, conjugate base here in just a second. So you may want to go ahead and draw an arrow. Draw an arrow that connects HCl to Cl minus. Okay, so HCl to the Cl minus. That helps you visualize and see what change happened to the HCl comparing the reactant side to the product side. What we see occurs here is the hydrogen was donated because, again, we see that on the product side it is no longer combined on that with the Cl. So in this case, hydrogen is, again, always what we're looking at for movement here. And because the HCl donated the hydrogen to the H2O, that classifies the HCl as the acid here. In this next example, NH3, we're going to connect that to NH4. So again, connect an arrow NH3 to NH4 to help you visualize what we're connecting. If we look at the formula, it went up in quantity of hydrogen, meaning it is a proton acceptor. And so because it's a proton acceptor, again, proton being the hydrogen, bases accept protons, and so this again is classified as a base, as where with the Arrhenius model, this would not have been a base. So I have a trick to help you remember, and that's the acronym BAD. BAD meaning base accept, acids donate. And it's all about what is it doing with hydrogen, okay? Interesting enough, water is interesting in that it's H2O, so chemically it contains hydrogen. And if we put two molecules of water together, it can result in H3O and OH. What's happening here is one has been the acceptor of a proton, while the other then is the donator. So water can act as an acid, and water can act as a base, which will be interesting here as we get into the little bit that's left for this topic. And so water can be classified as being amphoteric in that it's both acts as both acid and base. That leads us to two other terms besides the Bronsted-Lowry acid and the Bronsted-Lowry base, and that is the conjugate acid and the conjugate base. A conjugate acid is the product of the base. So the base is what is going to form this conjugate acid. And it's formed because the base accepted hydrogen. The conjugate base is the result, the product of the acid giving up the hydrogen. So here we have a labeled reaction. We have the acid. Again, we know it's the acid because of the presence of the hydrogen here. Comparing it to the product side, this is a donation of the hydrogen. So because it donated, using that acronym BAD, that makes it the acid. Now, if you read the reaction instead in the reverse reaction, because this double-headed arrow means it's a reversible reaction. Reactants can become products, products can become reactants. This conjugate base is really, the conjugate tells me that it's a product, but the word base tells me it's a proton acceptor. Well, if we read this equation from right to left, that tells me that we went from having no hydrogen ion to it accepting a hydrogen ion. And again, bases accept. If we read this equation left to right, the base took in a proton. Bases accept protons. But on this side, if we read this from right to left, we see that it donated. So your acids become conjugate bases. Bases become conjugate acids. So here I've got it labeled and stuff because of the Hovercam being goofy at this point. But what I have going on is NH4, if I connect it to NH3, this is what it started with and this is what it became. We can see that it went down in its quantity of hydrogen. Thinking of the acronym BAD, that tells me that acids donate. So because this reduced number of hydrogen, this is an acid because it's a proton donor. Water went up in hydrogen quantity, so it was an acceptor. Bases are acceptors. Looking at it in the reverse direction, if we read right to left, NH3 leads to NH4. That means this is a base because it was accepting. So acids become the conjugate base because in the reverse direction, it becomes a proton acceptor. The base here became the conjugate acid because in the reverse direction, H3O drops in number of protons because it gave up a hydrogen, and that is a property of an acid. So acids become the conjugate base. Base becomes the conjugate acid. Here, same thing. Hydrochloric acid, HCl, became a conjugate. Let's see, I've got this goofed up. Let me see if I can fix this while staying in here. I was trying to click and drag and change slides, and obviously that did not work out for me. Okay, now I think we're fixed. And display setting, duplicate. There we go. Okay, so HCl, what we see happen here is HCl became Cl. What happened is that it was an acid because it donated a proton. NH3 went up in proton count. That means it accepted, therefore that is a property of a base. So in the reverse direction, NH4 is a donator, which makes it a conjugate acid. Bases become conjugate acids. Conjugate bases come from acids. Okay, so as long as you know your acid and base, it's easy to then eliminate what's conjugate in terms of the acid and base. You will only have one acid, you will only have one base. Those will always be on the reactant side. Conjugate acids, conjugate base, you'll have one of each, and those will always be on the product side. Let's hope I got the arrows right and everything in the next one. So OH, and if you want to go ahead and add, there should be a -1 charge here. When I set up and typed the notes, that got left out, but it's the hydroxide anion. Here, it's a base because it accepted a proton. It went up in number of hydrogens, therefore it's an acceptor, which is a category, a property of base. That means on the product side, that makes this my conjugate acid. HCN went from having one proton to none in terms of the hydrogen. And so because it donated that, acids are donors. So again, in the reverse direction, that makes this the conjugate base. So again, conjugate acid and base are products. Acids and bases are on the reactant side. Please contact me if you have any questions.